This video will review Euler's formula for complex exponentials. So let's imagine we have a number which is e to the ikx. So I, as we said in the complex numbers video, is the square root of minus 1. So I is an imaginary number. So if we have a number which has both an imaginary and a real component, we can imagine plotting it in what's called the complex plane. So all real numbers fall along this x-axis. All imaginary numbers, which are real numbers times I, fall along this imaginary axis. And if they have some component of each of them, then they fall somewhere in the plane. This whole entire plane being the plane of all possible complex numbers. So Euler's formula is that the number e to the ikx is equal to cosine of kx plus I times sine kx. Now at first this may not look straightforward in terms of what it means and what those consequences are, but this is actually quite important and comes up a lot in quantum mechanics because of the prevalence of complex numbers in quantum mechanics, and gives us some very useful relationships that we'll see down the road. So first, the real part of e to the ikx, so if a complex number c is a plus bi, the real part of that is a, so the real part of e to the ikx is cosine kx. So if we have some theta here, which is equal to kx, we have some theta here, and in our plane, as we're going around here, the real part is going to be a cosine. So if you imagine this as a constant loop which is orbiting in this circle here, as we go around e to the ikx, then the part along the x-axis is the cosine function. Then the imaginary part, if this is c equals a plus bi, the imaginary part of a complex number is b, so that value is sine kx. That's the value along the y-axis here. So that's going to be a sine function as this circle goes around and around. Okay, so one thing we can notice here is that since sine and cosine are periodic, e to the I kx plus 2 pi is going to equal e to the ikx, because sine and cosine of kx plus 2 pi equals sine and cosine of kx. That's equivalent to taking this circle and rotating it around 360 degrees. Same thing if you go minus 360, same thing if you go minus 720, positive 1080. Any integer multiple of 2 pi that you go around the circle, you end up at the same number. So that's an interesting thing, is that there aren't many numbers that when you take them to a given power are going to repeat over and over again under certain intervals. The magnitude of complex numbers was equal to their complex conjugate times themselves. The complex conjugate of e to the ikx is e to the minus ikx. So complex conjugate times itself is equal to e to the ikx times e to the minus ikx, which is e to the 0, which is 1. So the magnitude squared of e to the ikx is 1, so the magnitude of it is 1. So you'll notice as we've represented this diagram here, in polar coordinates, kx equals theta here, and r equals 1. So it's always a distance of 1 from the origin in the complex plane as it rotates around and around clockwise as kx goes up. Another thing we can derive from this relationship is the values of cosine and sine in terms of these complex values. So e to the ikx plus e to the minus ikx over 2 is the real part of e to the ikx, which is cosine. So cosine is e to the ikx plus e to the minus ikx over 2. Similarly, sine is the imaginary part. The imaginary part of a complex number is itself minus its complex conjugate over 2i. So sine of kx equals 1 over 2i, e to the ikx minus e to the minus ikx. So in that sense, you could imagine all exponentials of e as a special case of e to the ikx, and you could imagine sine and cosine as special cases of the complex exponential. So what else of note? So e to the I 0, so kx equals 0, theta equals 0, we're right here. That equals 1, we're a real number. E to the I pi over 2 equals I, up on the plus y axis. e to the I pi equals minus 1. So go 180 degrees. We're at minus 1 over here on the real axis. And this is the result which is called Eulers Identity. So e to the I pi plus 1 equals 0. Mathematicians freak out a lot and call this the most beautiful equation that there is. Maybe you agree with them, maybe you think that's mathematicians being odd. Either way, it's a neat little result. So e to the I 3 pi over 2, 270 degrees, counterclockwise from the positive x-axis, is at minus I. And then e to the I 2 pi, we have rotated a full 360 degrees, and we are back at 1. So those are the values we get as we go around the circle that are either purely real or purely imaginary. Everything else in between is complex, having both real and imaginary components.